ఏది మేడం? ఈస్ చెప్పండి. Academic Council and VOS member at several universities. On తీసేయండి. హలో 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 హలో
హలో హలో
గేట్ దగ్గర డోర్ దగ్గర లేరా? ఇది బాగుంది, బాగుంది. డిఫరెంట్ సార్, క్లాసీగా కనిపిస్తుంది. గర్ల్స్ చెప్తే రాలి, అందుకే
Hello, 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 hello. అదే అది టీమ్స్లో మేడం వాయిస్ బయట ఎక్కడి నుంచి క్యాప్చర్ అవుతుంది చూడు. హలో, 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 హలో.
Yeah, hello. Hi. Hello.
హలో రావట్లే. హలో
Yeah, hello.
Hello. Hello. Good morning, sir.
హలో హలో సార్, గుడ్ మార్నింగ్. వస్తుందా సార్? ఓకేనా?
Good morning, dear students. I request all students to maintain discipline, settle down quickly. We'll be starting the inaugural session very soon, but please follow certain instructions. When the inaugural is going on, we expect all the students will maintain discipline. You shouldn't talk, right? Because you are representing the brand of Vardhaman, right? So remember that. Good morning, everyone. Emerging technologies provide new tools and techniques that can be applied to engineering projects, making them more efficient, effective, and sustainable. Respected dignitaries present in the room, heads, deans, faculty members, participants, and my dear students. I, Dr. Sangeeta Singh from Department of ECE, it's my pleasure to welcome you all to the inaugural of first EAIE International Conference on Emerging Technologies in Engineering and Management Sciences, organized by Vardhaman College of Engineering, Hyderabad, in association with EAI Core. The conference aims to assist as a complete memorandum for all the attendees, including both amateur and seasoned professionals from across the disciplines of engineering and management sciences. It's a great platform for scientists, engineering professionals, researchers, technical experts, and analysts to share their insights on engineering practices, standard operating procedures in technology implementation, research across all spectrums of business and management, and many more. To proceed with the inaugural, I would request the dignitaries to come forward and occupy the seats on the dais. To start with, I request Dr. J. Krishna Chaitanya Sir, General Chair, First EAI ICETEMS 2023, to come onto the dais. Next, I request Dr. Satish Kumar Sir, General Chair for First EAI ICETEMS 2023, to occupy the seat on the dais. It's my pleasure to invite Dr. P. Nageshwar Rao Sir, Head Department of ECE, to come onto the dais. I cordially invite Dr. J.V.R. Ravindra Sir, Principal, Vardhaman College of Engineering, onto the dais. It's my pleasure to request our chief guest for today, Dr. A. Krishna Kanth sir, Director AMS R&D, OSRAM India, Hyderabad, to come onto the dais. Thank you, sir. I request all of you to occupy the seats. To continue further, I request Dr. J. Krishna Chaitanya, sir, General Chair for the conference, to deliver the welcome address.
Very good morning to one and all. At first, I'd like to thank the management for giving this opportunity to organize the first ICETEMS conference at Vardhaman College of Engineering. So in regards, we started this journey in the month of September 2023, and now we are in the execution mode. So when we started this, so we communicated the European Alliance Innovation Society for the indexing part, and we had a lot of discussions on that, and we come across with the 187 papers, and we shortlisted only the 55 papers. So the acceptance rate of the EI conference is just 30%. And the conference is have with 3 different reviews, 3 peer reviews are there. So for that, we have a good team. We identified a good team in the internal as well as the external, and we pulled almost all 150 reviewers across the globe. So in this regard, I would like to extend my thanks to the coordinators who worked in the pooling of the reviewers across the globe. And coming to this, the journey, so we have a lot of issues we have seen, a lot of challenges we have seen in the reviewing process, and we come across all those things. And now we are ready with the proceedings, and it will be indexed by the December 2023. So with this a short welcome, I request all the dignitaries extend their cooperation in execution of this conference in the wonderful way. Thank you once again.
Thank you, sir. Now I request Dr. Satish Kumar, sir, General Chair for the ICETEMS conference, to address all the participants and students.
Good morning, all of you. Respected today's chief guest, Krishna Kanth garu, and our principal, Dr. J.V. Ravindra garu, head of the department, Dr. P. Nagesharao, and my colleague, General Chair, Dr. Krishna Chaitanya. A warm welcome to you for all the faculty, heads, deans, and as well as the paper presenters here to the ICETEMS conference inaugural function 2023. So I want to brief you about how this was happened, organization of this event by the Department of ECE. So as you know that our beloved principal has taken charge as a principal past 3 years back, his main emphasis was academics and research. So he encouraged the Department of ECE to organize different conferences. This is the 3rd conference we are organizing in Department of ECE in past 3 years. In December we are going to organize another one named as Broadnets, and July 24 also we are going to organize one conference. So with that encouragement, the research publications in Vardhaman increased enormously, and so that it will helps a lot in the growth of the Vardhaman. So this is a good conference where all the participants, those who have submitted their papers, can present and get the good recognition throughout the world. So with this, I thank the management, principal, and the head of the department to conduct this event, and we thank all of you. Thank you very much.
Thank you, sir. And surely we all are looking forward to many more conferences similar to this. Now, I request Dr. P. Nagesharao, sir, Professor and Head Department of ECE, to address everyone.
Today's chief guest, Dr. Krishna Kanth garu, Director IITH Design, and our beloved principal, Dr. J.V. Ravindra sir, my colleague Dr. Satish and Krishna Chaitanya, and faculty, participants, and my dear students, very, very good morning to all of you. On behalf of the department and organizing committee of this ICETEMS, I welcome you all to this first international conference on emerging technologies in engineering and management sciences. As Chaitanya told, very good response is there from all the researchers in all the corners of Andhra Pradesh, Telangana and other states. Definitely, this type of conference will help the researchers to present their ideas in a platform. Previously, when a conference is being organized, the conference hall is filled with the presenters, keynote speakers, delegates, and panel members. So actually it is a wonderful opportunity to researchers to present their findings. Presenting, as far as my opinion is concerned, presenting a paper in a conference will have more weightage than publishing a paper in a journal. Because when you are presenting a paper in a conference, the delegates, panel members and other researchers will be knowing what is our idea. Previously it is actually happening, the panel members and other researchers, they tell them this is not the right way, whether your approach is correct or not. I have attended number of conferences and presented papers in international conferences where I got very good ideas, suggestions when I am presenting the paper. That is actually ultimate idea of presenting a paper in conferences. Even my students, of course, if you look at the students of UG and PG, it is made mandatory to convert their projects into papers, so that the students will be knowing how to present their findings in the form of a paper, how to present abstract, how to analyze the results, how to conclude it. Simply it is not doing a project or not doing anything else. So unless you keep your findings in the form of a paper, so you will be consolidating the work that what you have done. So that is the idea of writing a paper and publishing or presenting in a conference. So we have conducted already 2 conferences. This is the 3rd conference, which facilitates the researchers, students and faculty to present their ideas before the other researchers, so that the other researchers will be knowing what is being done, so that they can continue. It is not only to present their ideas, it helps others to extend their works. That is the ultimate idea of conducting the conferences. So this conference definitely will help the other researchers, my students and faculty a lot. I thank the management, and I should appreciate the General Chair, Satish, and DMK Chair, Krishna Chaitanya, and of course our beloved principal keep supporting us in conducting this type of workshops and conferences. So I thank one and all. Thank you.
Thank you very much, sir, for your address. We have one distinguished guest who has joined online, Dr. Sachinandan Mohanty, sir, who is professor in CSE, VIT AP. He couldn't join us in person because of some health issues. We welcome you, sir. Now, to continue further, I request our guest of honor and principal for Vardhaman College of Engineering, Dr. JVR Ravindra, sir, to address all the participants.
Right. So, good morning to everybody. Thank you very much, respected dignitaries on the dais. My friend, Dr. Krishna Kanth, thank you for accepting, sir. I am very sure that you know how hard work he has done the last 1 year to conduct the 19th IEEE APC CAS conference. They had a very, very tough time. I was the publication chair, but my role was very, very, very little in that conference, but he was the organizing chair. And you know, it was very hectic time last 1 month, but still you have accepted my request and you are here. Thank you very much, first of all, for your time. So, other dignitaries on the dais and the other members, Sukanya Madam, Head of the Department MBA, and other dignitaries. Couple of points just would like to bring to your attention, that to some extent your classroom education will help, but beyond that you have to experiment a lot. Whatever the things that you learned in the class, you get only 10 to 15% of chance to execute them in your laboratories. But the other way around, you have to extend your work into the research. That means that you have to find out a better solutions always. Research is a simple thing that you have to research. That's it, for a better solutions. Open a problem that was closed 10 years ago, that is a research. Close a problem that was opened 10 years ago, that is also a research. But the research institutes, the ideas, always look for the better solution. You may not be able to give the best solution always, that may not be possible, but always you have to think for the better. So better, better, better. So how do I understand whether it is a better solution or not? We have to start, exhibit our work through conferences, through journals. Journals are a little the other side of the coin, but initially, whenever you get an idea, you just have to convert that idea into your technical English and then put all your efforts in writing the algorithms and then try to executing it and then, converting into a simple paper and submit that particular paper into a conference. It really doesn't matter whether your paper gets accepted or rejected, but only the best thing that what you get is the wonderful reviews. And based on that reviews, again, you can, redo your work and then start doing it. That's how, sitting at one particular place, you always get the international exposure. So that's how you have to get into your own, domain and then start working on it. So this is how actually, most of the institutes, IITs or NITs will do it. There is nothing more than that. How they are able to success in the sense they always think and they start publishing their work. And gone those days where the institutes are expecting your work when you are doing the PhD. But if you really go for any big companies like any companies in the field of VLSI, they don't need degrees, by the way, right? And they don't need 10 CGPAs. But what actually they need is the intelligence. So how best that you can work on a particular idea, and then how do you make it fast, and TTM, time to market. So these are the things that always we have to focus. That's the reason many conferences that we would like to conduct, and we will also encourage the students to attend the conferences so that you develop the knowledge which is outside of the classrooms. That's the main essence or the main motivation behind the conducting the conferences as well as the attending the conferences. And when we do these kind of the conferences also, we will invite many people from the industry and they try to fill the gap between the academia versus industry. Now today you will see from him that there may be many cases that he may discuss, but the point is that most of the cases may not be even looked into the classrooms. So therefore there is some gap, challenges, opportunities that we have to always understand and then go forward. So take these opportunities whenever you get a chance. Try to attend, try to listen these kind of the events, and then start working on your ideas. So thank you very much for your time, and good luck to all of you.
Thank you, sir. Thank you, sir, for emphasizing on the significance of research and how every conference plays a platform where we can have exchange of ideas among the students, the authors, the researchers, and other eminent personalities attending the conference. Now I request Srilata ma'am from EC department to introduce our chief guest for today.
Thank you, ma'am. So Dr. A.G. Krishna Kanth sir is currently the Director of Analog Mixed Signal R&D at AMS OSRAM Group. He is an IEEE Senior Member and currently the Vice Chair for IEEE CAS and EDS Hyderabad Chapter. He received his PhD from IIIT Hyderabad. He finished his BTech and MTech from IIT Bombay with specialization in microelectronics. He was awarded President of India Shankar Dayal Sharma Gold Medal and IIT Bombay Student Roll of Honor in 2002. Analog IC design is his passion, and his specialization includes sensors and sensor interfaces, high performance analog signal processing, power management for automotive and consumer semiconductor IC design. He is an adjunct professor at IIT Hyderabad and Digital University Kerala. He is an academic council and BOS member at several universities. He has 14 patents and 11 IEEE publications. He is one of the designated associate editors for Transactions of Circuits and Systems 2 for 2024 and 2025, and the organizing chair for the prestigious APCCAS 2023. Now I request Dr. A.G. Krishnakant sir to address the gathering. Sir, please.
Good morning, everyone. First of all, thank you for inviting me. Principal Garu, Dr. Ravindra, who is a very good friend of mine, and to the dignitaries on the stage, and also to Dr. Sachidanandan Mohanty Garu, who has joined us online, the general chairs of the conference, and head of the department ECE. Thank you for having me here. It's always a pleasure to be interacting with the students, and especially to present something to the students on whatever little we know while working in the industry. Let me congratulate first on really organizing this conference. See, one of the key aims, according to me, in a conference is also that you can really multiply your learning by not only focusing on your presentation. Right? I'm sure you have a paper or you want presenting a paper, but then also be part of all other sessions. Listen to them. Because I'm sure there are like 100 different ideas that will be presented in this conference. Several students, several ideas from different parts of this region will be presented here. So please sit through them. Listen to them. If you see that there's somebody who's already working in your area of interest, something similar to the work that they've already done, go talk to them after the presentation. Really network. The whole point of having a conference, in bringing people together, is really not just to be a silo and then look for your presentation, you're done, okay, you have your paper, and then okay, +1 count on your CV. That's not the whole point. The point is also to multiply your learning, make networks, network with people. This includes not only the students but also the faculty members. Really reach out to people who are working on similar areas of interest. Talk to them, understand the challenges, discuss together. And it could be possible that when 2 or 3 of you sit together, collaborate. It doesn't matter whether you are from one university or another university. Collaboration is the key, whether you are in academia or industry, to be able to deliver a good quality of work. It's absolutely necessary to be able to collaborate, and then together maybe 2 or 3 of you can write a much better paper, work on some common goals and then submit it to some great paper. So make sure that you network during this conference, have a good learning time, and benefit from this really exponential learning process. That's the whole essence of being participated of the part of the conference. So thank you so much again for the opportunity, and then I'll talk more about what we do, who we are, and then so on in my next session. Thank you very much.
Thank you very much, sir. Sir is a big bundle of knowledge. So we have his keynote talk after some time. Now I request all the dignitaries present on the dais to come forward and release the proceedings of conference in terms of souvenir. I request all the dignitaries present on the dais to felicitate our chief guest, Dr. Krishna Kanth, sir. Now I request the faculty members present in the hall to come forward for a group photo. All the faculty members, please come forward for a group photo. Thank you, everyone. Now it's time to listen to the eminent chief guest who has joined us and accepted our request. I request Dr. Krishna Kanth, sir, to deliver his keynote address to all the participants and students. Sir.
Okay. Can we start now? Okay. Okay. So again, good morning, everyone. The title of my talk today is about CMOS VLSI design, challenges and opportunities. Okay. Now, how many of you have heard about VLSI? Okay, quite a few of you. Okay. How many of you have heard about CMOS technology? Okay, great. So let me go to the agenda slide. Okay. It's not receiving the signal. Pointer. It's coming. Yeah. Okay. So the title of the agenda will be about, let's talk about why VLSI is a hot field, and VLSI technology challenges, IC design flow, so integrated circuits design flow, followed by understanding some application requirements or real life examples, something that you probably see in your daily life, then Q&A. So the theme of my talk is summarized in one line here. Okay. How do you guarantee that 1 billion devices designed and manufactured today, remain working in application for the next 10 plus years with acceptable performance? It's a very complex question. First, I'll talk about the keyword 1 billion devices. So here we are not talking about one single design or a device or an application. I come from a consumer domain, so which means all the sensors that go into mobile phones. Okay. I'll give you an example later as well. And if you look at the number of mobile phones that are being sold today, in terms of hundreds of millions of phones are being sold. And if a sensor or some product has to go into that, you need to be able to design and also manufacture. Okay. Now, I'll give a quick example. How much time does it take for you to maybe go to the lab, build a small amplifier using maybe LM324 or something? Any guesses? Just go to the lab, take one of those ICs. I'm sure you would have done as part of your coursework, right? How much time does it take to build an amplifier? Small amplifier. Yes, 10 minutes. Somebody said 10 minutes, okay? So let's do a simple math. How many can we do in 1 hour? 6. 1 day? Come on, 24 into 6. 144. Very good. How many in a year? Take an approximation. 150 into about 400, right? About 6 lakhs, right? So if you go with that pace and you work 24 hours a day, non-stop, then you're going to test 6 lakh devices in a year. And what we are talking about is testing, design, and validation of 1 billion devices. Okay, so now just see the scale. So this means we need to do something else compared to what we are used to in the lab to be able to design, manufacture, test, and deploy this in an application. The second part is, how do you make sure that something we design today remains working in the application for next 10 plus years? Okay? So we don't have time machine. Like, people who are writing code in software, right? Let's say you run a program, you get some errors, code dump, and so on. And then you probably go back, look at your code, and then correct the syntax error, run it again, trial and error method until you get your code completely finalized and everything is running. Great. Now think of the same thing from VLSI perspective. Once you have manufactured something, it's a physical piece of hardware in your hand, and you power it up and it's not working. What do you do now? How do you debug? Let's assume something is working today, and I'm sure even during my undergrad, I also faced several issues, and I'm sure you would have faced the same thing. During your lab viva or lab examination, you would have shown, maybe when you want to demonstrate to your faculty member, you would have said, "Ma'am, it was working just yesterday. I don't know why it is not working today morning." Right? Did you face this issue? Yes or no? Yes, I faced this several times. Okay. Now, if we are doing something if we're manufacturing something in a mobile phone, we don't have an option to say, "Oh, it was working yesterday. Something went wrong and it is not working today." Right? We don't have the choice. So this means we need to ensure that by design, the way we manufacture it, the way we test it, the way we deploy it in the application, it has to work for a certain amount of time. Now, how often do you change your mobile phones? Yes? 2-3 years. Somebody like me, maybe 5-6 years. Okay? How often do you change your car? Yes? 1 year. Rich kid. Others, I think average maybe 5 years, 6 years, 10 years, right? Again, somebody like me, I will change 10, 12 years, one car maybe, okay? Okay. Now, so this means the same circuit, the same application, the same sensor interface that is designed in a mobile phone is going to have a different set of lifetime requirements compared to the same sensor that's being designed in a car, compared to a same sensor that's getting deployed in a Chandrayaan 3, right? It's the same sensor, probably an amplifier or some analog to digital converter or a sensor interface, something. So the quality or the lifetime requirements while we design something are distinct and different with respect to the product that it is getting into. That's the thing that we need to understand. So each product, everything that we do in the design, in the VLSI, always has some lifetime requirements, a mission profile. I mean, how long should the circuit be working in the field? And that will determine a lot of things on your design side. And this will be a central, I would say, the background theme of my talk. What is it that we're going to do to make sure that we're able to manufacture something mass production, cost effective, high performance, and making sure that we can have this application working for several years in the final application. Okay, first, why is VLSI a hot field? Okay, before that, I want to talk about innovation. We always talk, this is a very common word. Everybody likes to talk about innovation, and conferences like this are all about finding new ways of solving problems, new ways of optimizing your systems. So what does innovation mean to us? Okay. So first thing is to understand what is the motivation purpose of your innovation. Why are you doing it? Oh. Then who needs it? Okay, you are innovating something, but there should be somebody who should need it. There should be some problem which really needs your solution. So what are the use cases? Why is the innovation important now? Let's say you're doing on something, something fancy, crypto computing or cryogenic engines, right, which are maybe very, very futuristic. Quantum computers, 20, 30 years later, they go to mainstream, and so on. So you have to be clear on when your innovation is going to be used. Is it in the short term or mid term? Accordingly, the effort should be focused on. Is it affordable? One of the big challenges in for researchers is we are so fascinated about our own solution to our problems that we simply forget that in the end, if this has to go into a product, somebody has to buy it, right? We all love iPhones, Apple iPhones, the brand, the buzz around it, but we'll all prefer OnePlus or Oppo, Vivo, Huawei, Samsung, and so on, right? While we love it, we like it. So cost matters. The price point where you sell, it certainly matters a lot. So we have to, as a researchers, it is also our responsibility to think whether the invention or the research that we're having is affordable, can be produced at a rate where the users are willing to buy. Some problem with this pointer. Okay. So is it scalable and sustainable? Okay. Can I now produce 1 billion? And most innovations are incremental in nature. So we are not some deep physicists or material science researchers. We are all ECE, EEE, electronics students, electrical engineering students. So most innovations are incremental in nature, which means we are trying to push the limit a little bit, go a little further, make sure that we optimize the system a little further, reduce my power consumption, power budget, energy budget a little further, so on. So most innovations are incremental in nature for us. So to start with, you see, the first electronic computer that was invented back in 1946 was 1800 square feet. So the size of a 3 BHK flat, right? And that was weighing about 27 tons. From there, this integrated circuits came, people found, smart people found a way to really shrink the devices. And eventually he said, okay, let's do something very, very large. And that's when they called VLSI, where I say, okay, if my number of transistors that are integrated are larger than 10,000, as an example, Then let's call it VLSI. And from 1946 to today, in fact 3 years before, 4 years before, 2019, a company called Cerebras came out with a IC which had 1.2 trillion transistors. Not billion, trillion. 1.2 trillion transistors integrated in a 46226 mm square. And this is the largest GPU has about 21.1 billion transistors. So now you can see 1946 to 2019, about 3 generations, right? And you can see the amount of scaling that has happened, right? So and whenever we talk about VLSI, it's important to just go back and understand the history, from where we have started and where we have come down. Now with this pace at which the innovation has happened, imagine what will be when you probably are in your maybe early 20s, late teens, early 20s, hopefully. And then when you come to about the next generation, 45s, 50s, right? This is going to be completely dramatic, different. Just look at the scaling, what has happened. So it's very important to understand, and this is where the conference like this helps you to, to mingle, think about problems that are being solved, think about the solutions, different solutions, different approaches that each authors or each persons are taking to solve their problems. Okay, so what was a size of a 3 BHK flat is now this on your finger. This is the integrated circuit, a very small IC. Now what drives VLSI innovation? I give an example of this. I think this is, somebody knows which model of this Samsung is? Samsung? S5? Yes? J series, okay. So I think this is probably sold 5-6 years back, I guess, right? Now, see these 2 tiny dots here, okay? So these are basically a transmitter and a receiver. So what this, and if you go inside the PCB, what you actually have is this. So this is there are two holes or apertures here. One is an emitter or a transmitter, other one is a receiver. The job of this is, whenever you get a phone call, right? As soon as you place the phone close to the ear, what happens to the display? Off. Why? No, why should you shut off the display? Yes? It might contact your screen, okay, but why does it need to shut off the display? Yes? Any thoughts? Which is the source of largest battery drain? Screen. These big screens, that is the biggest source of battery drain. So, fortunately, the way a human body is built is eyes and ears are perpendicular. So when you're holding it here, you don't need to see. And when you don't need to see, you should be able to shut off your screen to save power. Okay, and automatically it happens. As soon as you bring your phone close to your ear or hair or this side, there is a proximity sensor which is detecting. So you have a transmitter that emits IR pulses. Okay. By the way, which is the common device that you use in your home's daily life, which is an IR pulsing, IR light? TV remote, perfect, right? TV remote is it's an IR signal that you're using, and then there is a receiver in the TV that is now changing the channel, and it does what you want it to do. So similarly, this phone has a pulsar, the IR pulsing transmitter, which is emitting IR signals. And when I say IR, it is beyond the visible range, beyond 700 nanometer range. That's the reason why you don't see it. Okay, human eye is susceptible to only 340 to about 680. That's the nanometer where the visible light spectrum is there. So beyond 700 nanometer, that's the near IR, infrared range, and that is where we send these pulses. And based on the intensity of the received signal, which means as soon as you place closer, if the object to the sensor is closer, which means you are in a short distance to your ear, then the received signal, which gets reflected from your hair or ear or your skin, is much stronger because the distance is small. And if you are farther, the received signal on the receiver is weaker. So you look at the strength of the received signal and then decide whether you are closer to an object or you're farther, and hence use this information to shut off the display. That's the reason why, if you place your even finger or a hand on the screen, it shuts off, and then you remove it, it just goes on, right? So that's a proximity sensor. So now, what is driving these VLSI innovations? No, these are typical applications that we all use in our daily things. First, higher performance. We need better quality of products, lower power consumption, with longer battery life, to be able to scale things, miniaturize things, higher integration, small size, portability, reliability. We don't want to have large phones that we don't want to carry very large phones in our pockets. So these sensors, which there are 100 different sensors with PCBs, all the discrete components that are embedded in a typical mobile phone. I'm going to show one such example later on. So all of these have to be miniaturized. We also we want sleek phones, right? We like phones, but we don't want bulky, thick phones. We want compact, very thin thing. So once our requirement is to really have thin screens, thin phones, the integrated circuits that go inside this also needs to be made thinner, correct? You can't have very thick devices, large devices, 1 centimeter integrated circuit put in a 1 mm phone. We can't do that. So the entire ecosystem, the whole VLSI design needs to somehow miniaturize it, shrink it. Lower cost. I don't need to explain this. Smartphone deployability. Every single sensor these days, and every VLSI company wants a share of their products in the smartphone. That's because smartphone is the biggest deployable market in electronics industry. Everybody has it, right? Everybody has it. Maybe smartwatches now are becoming more and more popular as well, but then still smartphones are still the real Apple for all the semiconductor industries. CMOS technology is still considered as the mainstream. You will probably talk about bipolar technologies, GaN, silicon carbides, FinFETs, all of them, they are specific to certain application. The mainstream is still CMOS technology even today, and it's going to be the same for the next 25 years. Okay, so now before I move on to VLSI, I want to give a brief overview on different specialization circuits and systems. If you look at the electronics, the circuit systems on a whole, from a bird's eye view, 10,000 feet high, what does these circuit systems look like, all the different specializations? To start with, we have analog signal processing, which basically deals with interfacing with real world. Okay, when you talk, and I've heard people that come always say, okay, sir, this is the technology is going, there's a lot of digital content, will analog people survive? Okay, this is a common question that is always asked by students. Now, the only question I have for them is, when I ask you what is the temperature of this room, what will be your answer? Yes, you see there on the AC, 17 degrees, correct? You're not telling me 100011. If I ask you a temperature, you can't give an information, say, okay, temperature is 0111000, binary bit. No, you're going to tell me it is 17 degrees centigrade. What is the intensity of the light? What is the frequency of the sound? Real world is analog. Dot, period, that's it. So any electronic human interface system that deals with the real world has to have an analog interface. So analog is going nowhere. Okay, don't worry about if you're working on analog and one of your friends or 10 of your friends are in your digital domain doing some cool fancy stuff on FPGAs. Don't worry, we all will survive. I'm an analog man myself, so we all will have good careers. Next is about digital. So digital, the beauty about digital is you can shrink. The moment you are able to convert an analog signal into digital, if you have let's say you're playing an audio, MP3, each one have a distinct frequency, and these frequencies get easily corrupted. You can have noise, you can have interference coming from outside, which can corrupt your signal. So analog is very easy to be disturbed. It can get corrupted, and it has less immunity to external interference. The moment you convert something into ones and zeros, that's like written in stone. It's very difficult to disturb. It will be very difficult to make 0 into a 1 or a 1 into a 0. And that's the beauty of digital design. The moment you are able to convert something into digital, it is very safe, secure, you can encrypt it, you can do processing, you can now transmit it, you can now use it to shrink, go to a lower technology to really make the whole engine more compact. That's the beauty of your digital circuit. Third is RF. RF stands for radio frequency. Radio frequency is you can call it as a high frequency analog. Your mobile phone signaling, GSM, the Bluetooth, the Wi-Fi, the wireless LAN, everything, all these high frequencies are all in the radio frequency domain. Then comes the embedded. So embedded is, the embedded comprises of the firmware, FPGA, microprocessor, and controllers. So this is like the interface between hardware and software. So you code something and then put it in the hardware so that the hardware does its job. So this is like the software interfacing hardware. That's what we call it as embedded designs. Then memory, very important part of the whole VLSI industry. We all make our choice of phones based on whether we have 512 GB memory or 256 GB or 128 GB, how cost effective it is. So the memory, the capacity to be able to hold this, to be able to make a cheaper SSDs, the flash memories, the RAMs, all of these are extremely important for the VLSI design segment. EDA. So while we are talking about all of this, we need a way to be able to model these transistors. To sit in front of a computer, design something, use this transistor to design, and that is what the EDA does, electronic design and automation. So all the tools that use MATLAB, Cadence, SmartPice, Synopsys, Virtuoso, all of these are part of this EDA tools. Then it's testing and validation. So design, so once you have everything done, you have something in your hand, now you need to test and validate. So for that, we need to plan for a design for testability, DFT, characterization, and some products like an optical sensor. This needs to be characterized electrically in the lab, thermally across temperature, because your smartphone should work on Mount Everest. It should also work in Thar Desert, right? These applications are seeing extreme environments. That's the reason why you have to characterize these devices across the temperature of the application. As an example, if you're also doing something on engine control, you're making a sensor which is detecting the RPM of your engine, and it is deployed close to the engine, the temperatures at the engine can be as high as 125 or even 150 degrees centigrade. So the ICs, the integrated circuits that you're designing, should now withstand the application temperature requirements. Last but not the least, production, the reliability, failure analysis. So unlike software, when something is not working, some application or a chip is not working, right? Now the challenge will be, how do you know why something is not working? How do you debug? So in fact, just the way you go to your bone scan, if you go to, if you break a bone, you go to an orthopedic center and they do an X-ray to find out where, and if you have a dislocation and so on. There are ways, there are reliability techniques when you actually do an X-ray of the device, layer by layer, you remove it, you find out where you have a metal cut or what is our reason for this loss of performance and so on. So reliability analysis is a very, very important part of the whole VLSI process flow. Then we have ESD. ESD is the electrostatic discharge. Okay, this is the same phenomena as take a comb, wipe your hair, and then you make sure that the paper sticks. That's because there are charges, static charges built on this. And you might be surprised to know that while you're walking on a carpet, you can generate voltages and go and touch an IC in your lab. Right, in the morning, early morning, you are walking on a carpet and suddenly come to the lab, you touch an IC, you might see that IC might get damaged, something is not working. Suspect ESD. It could be that you might have discharged 8,000 volts onto an IC. Poor little thing will not survive. So every integrated circuit that you design needs to have an ESD protection to be able to discharge this high intensity voltage pulses, the short bursts of voltage pulses without disturbing the actual circuitry. Okay. Next is EMC. EMC stands for electromagnetic compatibility. So if you board a flight, air hostess asks you to shut off your mobile phones before takeoff and landing, right? And the reason is because each of the electronics circuitry that you're using emits a certain radiation. And these radiations, when they are in phase with critical signaling of your flight, they can really disturb the communication. And that's the reason why we are asked to switch off our electrical devices, go to the flight mode so that we are not emitting a lot of radiation. And then of course yield. Okay, with that, I want to go back to VLSI technology challenges. So CMOS technology, those of you who have read some textbooks on CMOS, you basically have NMOS and PMOS transistors, the two flavors. N metal oxide semiconductor, which has a gate, and so N you have gate which is built on a substrate, and then PMOS You have a P transistors which are built in an N well, which is in a substrate. So if you look at the basic structure, they will look like this. It's a polysilicon gate. You have contacts here and then these wells. But then if you do a snap, if you slice this at this, right, and then you go deep to do a entire cut of what is actually there in the entire substrate, the full-blown variant would look something like this. So this is your NMOS transistor where you have your source, gate, and drain. This is your P substrate, and you have PMOS transistor built in an N well. All these transistor needs to be connected back outside. You need to bring the critical signals to outside of your chip. So this is exactly like constructing a building, right? Your transistors are buried down in the cellar. Now you need some stairs to come to the first floor, which is metal 1. Then you need some stairs to connect to the second floor, metal 2, metal 3, metal 4, so on. And the top layer is what gets connected outside the chip. What gets connected outside the chip is the top layer. And like constructing a building, there are mechanical stresses, there are variations in these which lead to lot of unwanted effects. And the more you read about VLSI technology, the more you will understand about the non-idealities in this VLSI processing. One of the challenges that integrated circuits face is process. The manufacturing is again chemical reaction. We dope, we anneal, we heat it, and then we implant something at an angle and so on. So all these are chemical reactions, and they are done through certain machinery. And each of these machinery have certain inaccuracies. So the process variations of the semiconductor process leads to threshold variation. Threshold is the minimum voltage beyond which the transistor starts responding. Threshold voltage of a transistor. Then you have channel length variations, interconnect dimensions. All of this leads to a variability in your circuit. Second variability is your environment. So your supply voltage, whatever power supply that you're giving. For example, let's say you're building a sensor for your mobile phone. Okay. What type of battery does mobile phone use? Yes? Lithium ion, very good. So what is the voltage range of a lithium ion? Yes? Fully charged lithium ion battery. Yeah, somebody said 4? 4.1? Okay, 4.1, good right answer. Then, what is the lowest voltage? Sorry? When you keep discharging it, right? The voltage goes down. Typically it can go as low as 1.8, 1.2 volts. Now, when you're building a circuit, while the entire phone is getting discharged, the battery is getting discharged, your circuits need to be operational from 4.1 volt all the way down to 1.8 volt. So there is an intrinsic power supply variation, okay, which you need to deal with it. Plus there is a temperature variation. So I just read this table here. So for commercial applications, consumer applications, the temperature are 0 to 70 degrees. Industrial applications -40 to 85. And for military applications, so if you want to design something, some sensor for, let's say, DRDO or some space application or a defense application, the temperature range requirements are even higher. Okay. So -50 to 125 degrees centigrade. Third variation that you see in an IC is aging wear out. So transistors also age like human beings. Like you and me, transistors also age. Now, my first question on my first slide was, how do I ensure that the ICs that I'm designing on time 0 work for the next 10 years? Okay. I give an example to this. If you go to a cardiologist, have you known about the TMT test? Treadmill test, TMT. Did somebody visit a cardiologist along with your parents or so? Have you heard about a TMT test? Yes or no? Yes. So what they do in a TMT test is, you have a treadmill and they connect electrodes all over your body and they make you run. They slowly start increasing the speed. So you run, you walk, and then you see how you sense from the electrode how your heart is responding, how your heart rate is responding. So once you start running on the treadmill, your heart rate increases. And they do it every 5-10 minutes, they increase the speed to the point where you say, no, I can't do it anymore. And then they slowly get it down. And now based on how fast your heart rate is building up, and based on how fast the heart rate is coming back to normalcy, they detect and they tell you, doctor tells you, yeah, you're good with your heart, or if you are having problems, he might tell you, no, good, let's do an angiogram to see if you have some blocks, and so on. So what the doctor really is doing here, he's stressing your heart. He's putting the heart in, let's say, 40%, 50% higher heart rate than your normal operation, and then seeing how the heart is reacting to this stress and how the heart is recovering from this stress. Apply the same logic to a circuit. If I have to detect whether my circuit survives a 10-year mission profile, I need to stress my circuit. So what is done is really, how do we stress the circuit? If a circuit operates at 85 degrees maximum, I take it to 125 degrees centigrade, stress it for 100 hours or 1000 hours, and then based on the performance of the IC, we can say that, okay, if this IC survives 1000 hours at 125 degrees centigrade, it will survive 10 lakh hours at 85 degrees centigrade. So that is how the reliability models are built. So we do accelerated lives test to be able to test the reliability of an IC. And one key point to note for people who are working in VLSI is nothing is constant in an IC terms. The only thing that we know is two transistors which are designed, laid out similarly and see a similar environment, they behave similarly. That's the only thing that we use in the analog IC design part. Okay, now about the IC design flow. So the process of digital design flow, let's compare digital and analog. Digital design flow would mainly talk about, start with the system level design, a very high level, what you exactly want to build. Like for example, do you want to build an AI engine? You want to build an AI engine or an image processing algorithm, a face scanning ID, something that will scan your face and will do a match with the existing data. So you will define the system level requirements. Now you go back and then say, now I want to build an architecture. Okay, my architecture will consist of whether I need memory, would I need some DSP engine, would I need some high-speed data transmitters, serial, deserializers, and then so on. That's basically the architecture level. You go a little bit deeper, and then you now do a digital system level design where we can talk about the modules. You need a multiplier, you need an adder, so all of these sub-blocks. Then you go one step further and say, okay, how do I design my multiplier? You write an RTL code, and that RTL code is now synthesized, and what it's using and make a gate level netlist. So ultimately, we're talking about the gates, the NAND gate, OR gate, flip-flops, all of these come in the gate level design. Okay, you go a little deeper into the gate, you have this transistor level circuits. Basic NMOS, CMOS transistor with certain fan-in, fan-out, gate delays, capacitances, all of these come into play at the transistor level design. And a step down finally is the device, which is basically what you see. It's a source, drain, gate implant. Do the same thing for analog, ultimately you'll see the same thing. So whether it is digital or analog, there are different levels of abstraction, and this is what is used while defining a system. So the analog design flow, you start with what you really want to do, and then do a block level system design. So this means like the discrete ICs that you use in your lab, it could be a timer or an oscillator or an amplifier. You use this to build the block level design, then do the individual transistor level design of the block. You simulate, do a physical layout design, and then send it to production. Now what happens once you're ready for production, once you send it to manufacturing, right? What happens is that the ICs get fabricated. So this is a slice. This is a slice of your NMOS or a PMOS substrate, and all the circuits are fabricated. You can see these small checks here. It's a vertical and horizontal checks, the small lines. Each of these lines are cut, they are sliced. You cut it, separate them into single separate dies, and then now use it to bond it to the package. Plastic. This is what you see in your lab. A black plastic package with leads sticking out, right? That's the interface to your PCB. But then if you scrap that, if you remove the top lid, what you'll see is this single die here. Once you have this IC, design this IC, you debug it, you validate it, and then put it in the validation board for the products. So this is basically the flow what we use. Now let's see how we tackle a application. Okay, by the way, this is the wafer generation. You have all these wafers, and then you slice these wafers exactly the way you do here. and then you do a wafer saw. So you cut all of these slices using a wire saw and then generate all of these individual wafers. Each of these wafers, the circular wafers, have hundreds of different dies. So now in terms of cost, if you can design something in 1 square millimeter compared to 5 square millimeters, you get 5 times more devices per wafer, right? In the same real estate, if you can pack more dies by designing smaller ICs, you can extract many more, 5 times more the number of dies. So this means the cost of manufacturing one single die is reduced by 5 times. And that is what helps us to be more cost effective. This means as a designer, we have to make sure that we are able to shrink the die. Mask preparation, this is like a stylus, or a master cell. So this is what each of these steps, the way you fabricate, has a special mask. And this mask is like our, during Ganesh Pandal we see this, right? This is our mask. This is the template which is used to design the actual symbol. So this is like that, the template. And we need 50, 60 different masks. As you go to more and more complex technologies, right? As you go towards 28 nanometer, 60 nanometer FinFETs, 3 nanometer, 4 nanometer, the number of mask sets are increasing now multifold. Like for example, 180 nanometer, you might use 24 masks, 25 masks. If you go to 130 nanometer, you will go to 30. If you go to 65, you're at 35. And if you're going to advanced technologies, like 28 nanometer, 40 nanometer, you're probably using 90, 100. Those are the masks that we'll be using. That is why lower technology nodes, smaller technology nodes which are more advanced, are more expensive than more mature technology nodes. That's because number of masks, and each of these masks here costs us about $3,000, $4,000. So we're talking about a 4 lakh, 5 lakh per mask here in the technology part. And we use this mask, shine a UV light through this, have a compressor. So this is like a lens which is focusing all this UV light onto a very tiny area of your wafer. That is how a single die is manufactured. Okay? And you repeat this across all the different locations of the wafer, you get the entire IC. So, and that's what is this. This is your entire wafer with all the different circuitry which is etched through your the reticle or the mask. Now that is what is put in your IC and assembled, and these are the pins to connect to the external world, and what you end up with is this. And if you take this IC, slice it, maybe let's say put a drop of 2 of acid, decapsulate it, what you'll see inside is this. This is what you would see. So this is the die which is coming out of the wafer. You put it inside this plastic and then you connect them through this gold bond. You see these small tiny wires that are sticking out? These are the gold bond wires. They're actually made of gold. And this whole encapsulated package is sealed and it's given to you, and this is what you see in the lab. This is what you use it. So as VLSI engineer, what we are now doing is not only understanding how to use this in the lab, but really understanding how we will design this part. That is the job of the VLSI engineer. Okay? And one point, when you want to make thinner and thinner ICs, these gold bond wires actually have a height. They come as a loop. You connect to the die, and then they come out, and then connect to the lead outside. This is their external connection. So the height of the IC is dependent by whether you have how many bond wires you have. Because a bond wire connects it, and then it loops back and then comes down. So this is giving you a height. If you have to make thinner and thinner ICs, then we have to find a way to remove the bond wire. So how do I electrically connect the die into the package outside? That is what is the packaging or assembly technology. And in fact, there's one latest news that Micron is starting a assembly test packaging thing in Gujarat. Recently, you would have heard this news, right? This is what they will be doing. Find out advanced test assembly packaging solutions, and it's really a good start that we keep getting these PSAT centers in the country. Now, once you have the IC, in industry we are not characterizing this using manual methods. We have the IC built on a board. This is the board, and all the you would have seen this power supply, multimeter, oscilloscopes. Have you seen this in the lab? Yes, right? So you would normally tweak it manually, connect it, and then so on, right? But what is happening in industry is each of these instruments have a GPIB port at the back side. If you look at the back of this, they have a GPIB port. And that gets connected to a USB GPIB cable which interfaces to a computer. So everything you want to test or apply on the PCB is actually done through a LabVIEW software in the computer. Again, automation. You're not doing manually anymore. It's all automated through the computer, through the USB port of the computer, goes to GPIB, GPIB connects to your instruments, and instruments are able to now, you can change the voltage automatically. You can control anything that you want from the instrumentation. Okay, and I think this part probably is the last part of the thing, understanding application requirements. Now, before you start building an application, right, you have to think of 6 or 7 different things. First, understand the required accuracies. What is the resolution of your input signal? Are we talking about millivolts? Are we talking about microvolts? Are we talking about tens of millivolts? And accordingly, we have to design. What are the bandwidth requirements of your signal? If you're designing an audio sensor, right? What is the frequency range of an audio signal? Speech, audio signal. Yes? 20 hertz to 20 kilohertz. Very good. So you want to design an audio sensor. You know that your signal bandwidth is 20 hertz, 20 kilohertz. So you don't need to worry about anything beyond 20 kilohertz, right? Similarly, if you're talking about an FM receiver, what is the frequency of an FM receiver? Yes? FM receiver, Radio Mirchi, 98.3, right? That is megahertz. 98.3, 97.2, whatever here, they are actually megahertz. So this is transmitted at that frequency. So if you want to build a FM receiver, then you know that your frequency is between, let's say, 88 megahertz to 102 megahertz, 105 megahertz. So based on the bandwidth of your signal, the sensor or the application, it can be fine-tuned. Temperature range. What temperature are you operating the IC? Is it close to the engine? Is it on the dashboard? Based on that, your temperature requirements are going to be different. Power consumption. So is it a portable device that you use in medical electronics? Let me give you an example of pacemaker. How many of you heard about pacemaker? Right? What is the use of a pacemaker? What? Controls heart rate. Okay, so you know where the pacemaker is deployed? Where do they put in the body? Yes? Not in the heart. It controls the heart, but they don't punch a hole here. Where is it deployed? They put it here. Left side of your shoulder, somewhere here. Okay? They put now, think that you're designing a pacemaker. Let's say you design your pacemaker of this size, this big. Can you put it inside? No, right? So, pacemaker, the size of this pacemaker needs to be really, really small. Second, if your design is consuming hundreds of milliamps of current, you can't put a lithium-ion battery, like you're doing for your mobile phone, correct? It'll be a small cell, very, very tiny cell that goes here. And now imagine you're consuming a lot of power, right? Every 3 months, somebody has to get himself operated to replace the battery. And nobody's going to buy a pacemaker, right? Pacemaker typically has to withstand for about 6, 7, 10 years. And can the pacemaker stop? What happens if the pacemaker stops working? Done. Okay. Case closed. So these are the circuits that need to work continuously, low power for several years. So this means the power consumption requirements or design requirements for such components are extremely lower compared to when you design something in a car. Because car you have battery, large battery, a lead acid battery which is very, very large. So the application requirements are now guiding your whole design methodology of how you optimize the power consumption. Economics, how to minimize the cost, where do you do an appropriate partitioning of the system, what are the choice of external components, all of these determine your economics or the cost of your system. Sorry. Quality, how to test the system in the lab, how to monitor its health in the device while working, how to guarantee the lifetime of the IC. So there are pacemakers that give you alerts on your mobile phones these days that the battery is going down. There are self-healing circuits that are built people are coming with self-healing circuits, which means if the circuit is deviating from its performance, then there are automatic ways of sensing and correcting within the chip itself. You don't need to do anything. Automatic correction, automatic healing, self-healing circuits. Very, very interesting part of the VLSI. Then robustness, ESD protection, latch-up, EMI interference, and immunity. So all these play a role in deciding how we are designing a particular product. Let's talk about an application. Okay? Let's say smartphone. Okay, so as a smartphone user, right? You all use smartphones. We all use smartphones. What do you want from a smartphone? Yes, what do you want the smartphone to do? Directly RAM, huh? Access internet, okay. No, first let's talk about, do you want a bulky phone? Okay, how do you want your phone to be? Light, cool, thin, great performance, dead cheap. What else? Right? These are our, as users, right? These are our requirements. This is what we want from our smartphones. Thinner size, lesser weight, great battery life, reliable, affordable, whatnot. Right? All these are our user requirements. Now, what does this mean for an electrical engineer? Okay, somebody tells you, okay, I want to do this. Electrical engineering now translates this into things and say, okay, because I want smaller, thinner phones, the form factor or the number of components or the PCBs or the integrated circuits need to be small. Otherwise, it's going to increase the weight. So we have to integrate more and more components and use lesser number of connectors, low power modes, battery that is constantly maintained, and then integrated circuits which have reliability greater than 5-year lifetime. So this is the requirements now given to an electrical engineer or a system engineer. Now what does this mean for a VLSI engineer? Okay, this is what electrical engineer tells you, okay, now I need ICs. Boss, I need ICs which have this level of integration. So what does this mean for VLSI engineer? Very thin through silicon via ICs, ambient light sensors, proximity sensors, MEMS microphone for excellent noise rejection, fast battery chargers, right? People are advertising 10-minute charge, 6 hours talk, right? People advertise it on the phone, right? This means you need the fast DC-DC chargers, fast battery chargers here. AMOLED screens, great screens with better contrast ratio. Time of flight based cameras for object focus. When you're taking a photograph, you would select a particular region, you tap on the screen so that that region of the image now becomes focus, correct? You have portrait modes where you only look at the object and then blur the background. All of these are possible because of the hardware and software combination. Capacitive touch screens, fingerprint, face IDs. So see, from a user requirement here, the life is getting more and more complicated for VLSI engineers, right? Example, proximity sensor. So I spoke about this. As soon as you get a phone call and you place closer to the ear, the display shuts off, correct? Now, if you go back to the J5 or Samsung S5, whatever we spoke, 5-6 years back, S6, I guess, 6-7 years back, we had this nice transmit receiver. The sensors were all placed below this. This was our selfie camera. This was the microphone, and it was behind this plastic. Now, over the years, people, as users, we said, if I want to hold a phone, I am not worried about this plastic. I need full screen. As users, I want to maximize the screen to body ratio. I want the entire body to be a screen where I can watch nice videos, big videos. I don't want to hold an 8-inch, 9-inch phone on my hand, right? I don't feel comfortable doing that. So over the years, what has happened is, shrink, bring it closer, increase the display size compared to ratio, shrink further. All your OnePlus phone fans, you have this teardrop design, right? This is called teardrop design. This is a selfie camera. We got a request from, for the selfie camera, the place that is available. We had a lot of real estate here, a lot of place. Now for this type of cameras, we don't have any space. Where do I fit my transmitter receiver? Okay. And actually we have space only here. They give us small space and say, okay, you get 2 mm, design the sensor and put it here. Okay. So now people have become more and more aggressive and they said, no, okay, I don't want this. I want even smaller, shrink. And then selfie camera on this side so that it looks more cool. And this is our latest one. This is what we have today, right? The entire screen is a display. Now, we still want the selfie cameras. We still want to shut off the screen when we are pressing closer. So where do I embed my sensors? Where do I put these sensors now? I have to put it below the display, correct? There's no other way around. Now when I put it below the display, how am I going to sense the external light? Because the display is already bright. How can I sense environment light and adjust my display when my display is already light, right? These are now the challenges. And once you have a display, the amount of light we are receiving on the sensors, the amount of light that is getting transmitted or receiving is now reducing. Your sensitivity requirements are increasing. Your signal to noise ratios are becoming more and more tighter. Those are the challenges now we see while we build products for every generation of these smartphones. Now, what is helping us is a 3D IC technology. So it's called more than more. So we all know that there are the CMOS process what we use, right? There are many variants of this, 180 nanometer, 130 nanometer, 28 nanometer, all the way down. So what happens is that lower technology nodes or advanced technology nodes are more useful for digital circuits, where you can shrink closer, pack more and more transistors to be able to if you have to build an AI engine, you need a lot of data processing there, a lot of high-speed data processing. So this is only possible when you go to the lower technology nodes. But for analog sensing, you don't need the lower technology nodes. And now it's a question of how do you partition the analog part of your chip and the digital part of your chip. So once you build two different ICs, how do you bond them? How do you connect them together? Because if you keep doing several ICs, one after the other and connected, right, you're going to now increase the size. So people have come up with smart solution and say, let's not do a flat, let's not extend it on 2 dimension, let's do a 3 dimension. Take the die, take the bigger one, put it on the top, put it on the bottom, take another die, put it on top of it, another die, put it on top of it, and so on, and then find ways to connect it. So now that is what is the 3D IC integration, where all of these different technology nodes, the advantage of 3D IC is that you can design one die in 180 nanometer, another on 130 nanometer, this can be 28 nanometer, this can be 10 nanometer, based on whatever the requirements, process requirements are. And all of them being bonded or held tightly together in a very, very small area. And this is what is leading to NANI, which is the world's smallest digital camera module. This is done by my company. And the advantage of this is, it's basically a, have you been to any gastroenterologist for endoscopy? Endoscopy? Yes? No? Yes. So what they do is they insert a probe. You're asked to open your mouth, they insert a probe. This probe goes into your esophagus, and now it's looking at the image of the liver, your spleen, to see if you have some ulcers there. And it is able to transmit this data back to the computer on which the gastroenterologist can look at the screen. Okay? Now we all know to take a photograph you need light, correct? Yes or no? To take a photo, can you take a photograph in a dark light? No? And is there light inside the body? No? Yes or no? No. So now if I have to transmit an image or take a photo of something that's inside the body, what do? I also need to integrate an emitter, some light source. So this NAN-I camera not only has the camera but also has a small light source, all designed and done in a very tiny size compared to your matchstick head. And this needs to be disposable because it's especially during the COVID time, right? This is not something like a typical spoon where you just boil it in hot water and it gets sterilized, right? You can't just boil these tiny cameras. So these are disposable endoscope modules, which needs to be lower cost, almost one-time use, very, very tiny thing, and this was possible because of the 3D IC integration. So the reason why I'm bringing this is because just to give you a flavor of the amount of technological advancement that VLSI field has done over the years. That is the whole point of bringing this to you. And what's there inside is all memory, ADC, SPI, serializers, all of these are present in this tiny module. Okay. This is your Samsung S10 Plus teardown. So if you watch a video in YouTube on S10 Plus, right? This is your phone, and you can see that there are several different ICs from several different companies, all integrated with several discrete components, front side, back side, and you have, memory, mixed signal designs, mechanical thing, batteries, cameras, connectors, memory, all of them. And that's the reason why, the price of this is higher and higher. And each company, every semiconductor company in the world, every VLSI company in the world tries to get a share of this pie. That's all that we are doing. Okay, and since you're all students and who might somebody want to build a career in VLSI industry, I just want to give also some information on what are the industry skill set requirements. If you want to join a semiconductor industry professional in the product development, a typical product like this, let's say an Nano camera, is done by what are the skill sets that are required in the company to be able to do a VLSI product. And the list is very simple. All of this, marketing, product architect, analog, digital, EMC, ESD, reliability engineering, package, quality, application, sales, all of these. So each IC or a product that is designed or available in market is a cumulative hard work of maybe a few thousand highly trained VLSI engineers. And several such, hundreds of such companies come together to now build your phone that you're using. Okay, this is my last slide. So we all know necessity is mother of invention, right? So, and the journey from necessity to invention is very simple. You start with most solutions are found in biology. We have learned how to fly aeroplanes, and we have learned how to design drones based on the biology. Then you have, from there you go to laws of physics to see how you can make things work. We use algorithms or maths to be able to extract information, generate data for your AI stuff. And then materials and chemistry to be able to do the product actual design, to be able to withstand the temperature. From physics, we go to the electronics design. From algorithms and math, you build your software to be able to do that. And from materials and chemistry, you do the mechanical design. Now, while you do all this, there are two things that are very important is quality and safety and the cost. Once you have all of this in the right proportion, you have the invention here. Okay? So real life is multidisciplinary. There are no simple, straightforward problems. You think that, okay, I connect this resistor here and there, or I put up a 5-volt power supply, my life is all done. So the real life problems are extremely multidisciplinary in nature, and that's the reason why it's no longer about circuits, it is about circuits and systems. Thank you.
Thank you, sir. It's always wonderful to listen to you. The last slide in particular, I can correlate, right? You all can correlate with that. Why we people are studying physics, chemistry, maths and everything. Because our life is multidisciplinary. Many disciplinary engineering, right? You have to incorporate, integrate to come up with the innovative solutions. Thank you, sir, for accepting our request and delivering such an interesting keynote. You have rightly specified, like, our life is surrounded with complete digital systems. Everybody is using many digital gadgets, be at home or at college. Sir has stressed on what actually is inside the digital gadget, because it takes so much of innovations and developments to come out with such a minute, right, miniature product, depending on the requirement. So you see how much research can be done in that area, and you can come out with your own designs as well. Thank you, sir. Thank you very much.
So I want to end this with one question. So how many want to join VLSI field now? How many want to join the VLSI career path? Okay, not bad, at least 50%. So I think my job is done.
You can also understand with the recent developments, right? Semiconductor industry is now blooming. So you have lots of job opportunities there. And when you listen to such eminent speakers, you get idea, and you can decide your future career options also. You can talk to sir about internships or how to proceed, what kind of training programs you have to undergo, so that you can prepare yourself. Thank you, sir. Now, moving further, We have one online session now by Dr. Malaya Kumar Nath from NIT Puducherry. I request Jayalakshmi ma'am to introduce our next speaker.
Yes, good morning and welcome everyone to the plenary talk on of first international conference on emerging technologies in engineering and management science, organizing by Department of ECE in association with EAI. It's my privilege to welcome today's speaker, Dr. Malay Kumar Nath sir. He has completed BE in Electronics and Telecommunication Engineering from BPUT Odisha in 2003 and MTech in Electronics and Communication Engineering from IIT Guwahati in 2008. He has completed his PhD from IIT Guwahati on signal processing. Now he is working as an assistant professor in the Department of ECE, NIT Puducherry, Karaikal since July 2013. He was secondment to Asian Institute of Technology, Bangkok, Thailand by President of India for teaching error control coding in the year 2018 for one semester. He has more than 25 publications in reputed SCI journals and international conferences. And his research area of interest includes image processing, signal processing, pattern recognition, and VLS image processing. Now I welcome you, sir, to deliver a talk on evaluation of AI and ML trends for future generation.